All right, so this is Math 547. The official name is called Introduction to Advanced Calculus. Oh, sorry, the name is wrong. Sorry, it's called Advanced Calculus 1. I haven't updated this yet. All right, the first things I want to go through with you is the syllabus, okay? Now, here is the basic information about the syllabus. So normally I'm going to be in my office, okay, and in the Jabara Hall. And if you have any question, anytime, any day, and you can come to unless it's a lecture time, and you can come to my office. But I'm not so sure. Sometimes I'm busy. I have two offices. My personal office is 358. A shared office is 355A. Okay. And I have email. So if you have any question, email me. Okay. Or you can call me. And I prefer the email. Okay. Email communication is easier for me. Okay. So our class time is Tuesday and Thursday, and 4 to 5:15. And the office hour is after this, like after the class time, after the 15 minutes, 5:30 to 6:30. Now, here is one thing. So I was required to attend the chair meeting once a month on Thursday afternoon. That's conflict from the class time. So on that specific Thursday, I'm going to delay my lecture until 5:30. Okay. And I hope you'll be available. If you're not available and you can view the lecture video, you can actually review the video later. Okay. Now I'm going to announce that Thursday later. Okay. And so it's not a big deal. All right. Now for this class, you need to have 415. The prerequisite is 415 with a C or better. I think all of you have this class taken or something is equivalent to that. Right. Okay. So required textbook. Actually, there's no required textbook. Right. And so sorry, I haven't updated the name yet. It's not called a mathematical reasoning. It's called Advanced Calculus 1. And basically, most of the information will appear in the PowerPoint, my PowerPoint presentations. Okay, so you can see the recordings, so you will get the detail about this about the lecture. Another thing is so there are some other readings you can read by yourself, but however, it's not required. If you're interested, you can actually learn something from other books, like the first course in reanalysis, and also the elements of reanalysis. Okay, so there's two additional books you can think about. Okay, the course grade will be determined by so I'm going to have quiz, okay, chapter quiz. So 20% each, and final is 40%. Okay, so this means that for the, so I'm going to go over this detail later, okay. Now, homework assignment. The homework will be assigned during each lecture, and you must do your homework seriously because the chapter quiz will be heavily based on the homework problems, okay. But it doesn't mean that the chapter quiz problem will be exactly the same as the homework problem and you just memorize it. Or actually, at this time, I don't know whether we're going to in-person testing or the zone testing. I don't know. Okay, so I don't know whether it's a closed book or open book. We're going to see later. I'm going to decide this later. Okay, but however, homework is important, so you must study it and do your homework problem before next lecture. Okay, otherwise you may not prepare enough to join the next lecture. Okay. And now about the quiz exam, the chapter quiz, I'm going to have chapter quiz for chapter 1, chapter 2, chapter 3, and dates will be announced later. More information follows, okay. The final exam, I'm expecting the final exam will be in-person exam. That's Wednesday, May 13th, okay, 3 to 4:50. So that's about the quiz and the exams. And now if you have any compelling reason for missing a quiz or exam, you must inform me before the exam, all right? And there's some additional important academic dates you can look at by yourself. Okay, so that's basically on the general information from the syllabus. And in this class, in this semester, we are going to have 5 chapters for Advanced Calculus 1. So on the chapter 1, so we'll talk about R. R, what does R stand for? R stands for the real number set, okay? We'll talk about real number set and the completeness property. So today we're going to actually have study some concept, the related concept. Chapter 2, we'll talk about limits of sequences. And chapter 3, topology of Rn. Rn is the n-dimensional Euclidean space, okay? Then we talk about continuous function and differentiations in R. So some of the material looks like similar to calculus theory, right? So you took calculus 1, 2, 3. So calculus theory also covers something like this, continuous function differentiation. But actually, this semester, the advanced calculus is very different from the calculus, even though they are dealing with the same subject, okay? Okay, any questions so far?
On the tests, are we going to be allowed to use notes?
You mean the quiz?
Yeah.
Now, if I decide to be a Zoom quiz, the quiz, I mean, it's not an in-person quiz, okay? And then it's not going to be a closed book. There's no way I can make the quiz to be closed book. I can, right? So if this happens, so this means it's open book. So it means you can view anything. Well, of course, the notes and the textbook notes, yeah. Any other questions?
If we were to have in-person quizzes or exams, would we be allowed something like a note sheet?
No. If I arrange an in-person quiz, okay, then you're not going to. I mean, you cannot see any textbook notes on any other the course information.
Okay.
Yeah, but the in-person quiz, the problem is the classroom, the assigned classroom is not big enough to hold 21 people. Okay, so unless I divide it into 2 groups. So I don't know that yet. Okay.
Okay, thank you.
Yeah. So now I think we are in a position to talk about the background information about the advanced calculus 1. So here we're talking about calculus, but there's another word attached to it. It's called advanced calculus. So what's the difference between the calculus and advanced calculus? So this is the first thing I want to talk about. So basically, we have 2 kinds of calculus courses, okay? Now, you took Math 242 to 344, right? So this is calculus 1 to calculus 3. So this is the regular calculus series. So for the regular calculus series, so what do you learn? You basically, well, I'm going to list a few topics, okay? Like you learn functions and limits and continuities and the differentiation, like a derivative test. There's lots of application and so on. You learn a lot of things, right? Now, the key point is in the regular calculus theory, the focus is problem-solving procedure, okay? It's problem-solving. For instance, they teach you formula and rule. Of course, they also introduce why we have such a formula, why we have such a rule. But our focus is trying to teach you how to use these formula and rules. For instance, now if you look at this formula, you know what it is. This is called a chain rule. Now, if you find the derivative for combined function, composite function, f and g, okay, you take this derivative, then the derivative actually follow this formula. Okay, so this is the rule, okay? Now in the regular calculus theory, so this is done in calculus 1. They teach you how to use it, how to use this formula, okay? How to apply this formula to specific functions. For instance, like find the derivative for fx equals sine 1 plus cosine squared x. It's complicated function, but once you apply this chain rule, you can find the derivative eventually because you know the derivative, basic derivative formula for sine and cosine, and then you can use this rule to get it, right? So that's the main focus of the regular calculus theory, focusing on how to solve problems, how to use this rule and how to solve problems. Okay. Now here we talk about advanced calculus. Advanced calculus is very different. They're not focusing on the application. They are not focusing on how to use this rule. They're focusing on proof of theorems. Okay. Well, so advanced calculus may deal with the same thing, like this, the same formula will be dealt with in advanced calculus 1. Okay, it's the same formula. But however, we are not focusing on how to use this formula to specific function. Instead, we ask the question, why does this formula or theorem hold? And how to prove this formula theorem. So that's the main things we have to talk about in advanced calculus 1. And this is important. Okay, now if you want to continue to, well, so this class, the Math 415 is a crucial class for math major, and you may want to continue, right, to like study more advanced class. And this class is very important. It's a basic. Okay. So now let's take a look about what subject I was going to cover by advanced calculus 1. Okay. So first thing is a real number theory. Now in the regular class theory, in the regular calculus theory, we don't worry about what the number theory is. We know what is real number. We don't care about the theory basically. But in the real analysis, in advanced calculus 1, this is the first things we want to study. And then again, we want to study limit, but this time this limit concept will be studied in a very detailed way. Okay. Then we want to talk about topology, because as you can see in chapter 3, we want to talk about topology in the n-dimensional Euclidean space, continuity, and the differentiation. Okay. So for instance, some of these things are in the regular calculus theory. Some of the things is not touched, like real number theory, topology, right? And also some of these things are just briefly touched, like continuity. Now remember how many lectures you studied are devoted to continuity, the concept of continuity in calculus 1. Maybe one or two lectures, right? But in this class, the continuity is a big thing. Okay, we want to take a month maybe to study the continuity like that. Okay, so this is what we have seen here is a difference between the regular calculus theory and the advanced calculus. Okay. All right. So now let's look at the course goal. So we have two goals in this class. The goal number 1, the most important goal, is that you will develop math reasoning ability in mathematical analysis. Okay. Just like in Math 415, you begin to develop some reasoning ability, right? Now in this class, you will continue to develop this the reasoning ability, especially in the mathematical analysis. Okay, like you're building the mathematical muscle. Okay, and so you can mature enough to take more advanced classes. So that's goal number 1. The goal number 2 is actually you continue to learn how to write mathematical proofs. Now 415 is devoted to teach you how to write proofs. But this class, you are going to write longer proofs, more complicated proofs. Okay, so that's goal number 2. Okay. All right, so we have 4 chapters, okay? Chapter 1, 2, 3, 4, 5. And today we'll begin to talk about the chapter 1, the real number theory. Okay, so now we're in a position to begin to introduce the theory. Okay, so in this class, I'm not going to show you the complete theory, but I'm going to teach everything we need in order to study the later chapters. Okay, we need to know a certain number of things about a number of things from this theory. Okay, now first let's begin to review some definitions. Okay, the definition about numbers. So the simplest number is called a natural number, like a 1, 2, 3. Okay, positive integer. So that's called a natural number. Now, if you're adding 0 into this natural number, then you get whole numbers. Okay, whole numbers. Then you begin to adding negative numbers, you get integers, right? So you learn this from elementary school. And then after the integer, you begin to, we talk about rational numbers. Rational. So how do you define the rational number? Rational number is basically any number can be expressed as a fraction. It's called a rational number. Okay. So for a rational number, and sometimes you can use fraction, sometimes you use decimal, finite decimal, like 0.63. So this 0.63 can be turned into a fraction. Okay. And also you can use repeating decimal like this 0.012 bar. That means this digit is going to repeat itself, okay, to the infinity. So all these numbers can be expressed into a fraction. So any number which can be expressed as a fraction is called a rational number. Okay. Now, besides rational number, we know that there are some number cannot be expressed as the fraction. That's called an irrational number, like square root 3, like a pi, like some digit like 0.10100110 and infinite with infinite decimal behind this, right? It's called an irrational number. So when we talk about real numbers here, we're not worried about integer. We're not worried about rational numbers. So these are numbers well defined. We're worried about the irrational number. The question is, how do you really define irrational number? You cannot just take irrational number as a number. You have to, make sense of it. So that's why we need to have a theory, what we call real number theory. Okay. So now let's begin to look at the issue involving irrational number. Okay. Now, the biggest issue, think about square root 3. Now, how do you define the square root 3? Okay, square root 3. So this is just symbol, right? It doesn't tell you what this number is, but mathematically, square root 3 can be defined as a solution to x squared equals 3. That's solution, okay? So when we talk about this, when we define square root 3 in this way, there is an immediate question. Whether the solution exists. Maybe the equation has no solutions, right? Now, remember in the Math 415, we talk about example. Okay, there's a Math 415 result. It says that if this solution exists, okay, the solution, if exists, cannot be rational. So this is something is proven in 415. So what does it mean is x squared equals 3. I don't know whether this equation has a solution or not. But if this equation has a solution, then that solution cannot be rational. So in a moment, I'm going to review the proof with you as one review problem, okay? So this result, the 415 result, okay, does not tell you anything about the existence of solution, right? So it doesn't tell you what is square root 3 is. It's only tell you the square root 3 may be an irrational number if it exists, but it doesn't tell you any property of this square root 3. Okay. So before I continue, I would like to review with you about the proof of the 415 result, saying that the square root 3, okay, if it exists, it's not a rational number. So that's a proof. So here, the argument is like this. So if x is a solution to x squared equals 3, we want to show that x is not rational. So here, I'm using this opportunity to review this argument with you. So what we're trying to do is we're trying to use what we call method of contradiction. So this will help you to refresh your memory about what is method of contradiction. So using method of contradiction would mean that you assume the opposite. That means you assume that the solution has a solution, which is rational. And then we're trying to derive a contradiction, right? Now, by assuming x is rational, what does it mean is any ration can be expressed by a fraction. So therefore, you may write x equal to m over n as a fraction, okay? With m and n integers, okay? Now, when we made this arrangement, we continue to make m and n so that this fraction is in the simplest form. What this means is, you see, fraction, okay? There are two fractions may equal, but however, the digits are different, okay? But however, there is one. It's called in the simplest form. This means that m and n has no common factor except 1. So we're using this fraction to express this x, okay? Now here we're in a position we're assuming that x is rational, and I'm assuming, and because of this, so x is equal to m over n for two integers without common factors except 1, okay? Then from here, I'm trying to derive a contradiction. Now how to do this? Well, the natural step, the next step is to plug in m over n into the equation. So you get this. And then you can see that I can remove the denominator to the right side. So you get m squared equals 3n squared, right? Now you have 3 appear. So this means that they're all integers. So this means that 3 divides m squared. And then based on a theorem in 415, so you know that if m divides something, m is a prime number. It divides square of integer. Then this prime number should also divide the integer itself. So 3 divides m, okay? Now, when we say 3 divides m, so this means m itself can be written as 3 times k for some integer k. Okay, so this is what we mean by something divides something, okay?
Sasa the value English, but
Excuse me?
Sí.
Any questions? Okay, so this means m equals 3k for some integer k, right? And then you plug in m equals 3k into the m squared position, the left side of the equations. And this gives you, because the square of 3k become what? 9k squared. And then this will equal 3n squared. Okay, so both sides carry 3. So I can cancel that 3. You get 3k squared equals to n squared. Okay, so now you see that not only 3 divides the m squared, now the new equation tells us that 3 also divides the n squared, and therefore 3 divides n, okay? So you see the logic. So combining all the previous 2 steps, you can conclude that the 3 divide both m and n, and this will give us a contradiction. Why? Because this contradiction to the selection of m and n, because we choose the m and n such that there are no common factor except 1. Now I'm getting a common factor greater than 1. So this is a contradiction, contradict to the previous early arrangement. So this contradiction shows that the assumption is wrong. Therefore, the argument, the statement itself is correct. So as long as x is a solution to x squared equal to 3, this will imply that x is not a rational number. Okay, so x cannot be rational. X has to be rational. But this proof doesn't tell you whether the x really exists, because in this result, there's assumption saying if x exists, then x is not rational. So I don't know whether x exists or not. Actually, in chapter 1, Advanced Calculus 1, chapter 1, we're going to see later, we'll have another proof show that actually such a solution exists. We're going to show you the existence proof later, okay? Okay, so now let's return to our issues. So actually you compute, you can see that square root 3. So here I'm just giving you the existing result. Okay, square root 3 really exists, which is equal to 1.7320508075. It's continued to the infinity. There's an infinite digit associated with x equals 3. Now, if you look at this expression, Do you think the square root 3 is well defined? It's not well defined because it's only defined a part of it. Because after 7, okay, there's a many infinite number of digits after that. Cannot be expressed here. That's impossible to express this here because the infinite number of digits. How do you express infinite number of digits? There's no such way. So this means that square root 3 cannot be defined just using decimal. There's no way. Cannot be defined as a decimal number. Okay. This number is purely just not well defined. So that's the issue with irrational number. So that's why we need to build the theory for irrational number. Okay. So now you see the issue, right? Okay. But however, there is a concept. I mean, there's an idea. Idea is to solve this problem, you have to use the limit concept. Now, how do you use limit concept? It means that this decimal number carries infinite number digit can be expressed as a limit of rational sequence. Now, what this means is that I can take this this number like this as a sequence. Like 1.7 is the first digit. The next one is I carry the second digit, 1.73, then 732, and so on. So I can create a rational sequence. All the number in this sequence are rational number, okay? So these rational numbers are well defined. And you can see that roughly, you can see this sequence in this range in this way, somehow approach this rational number, okay? So here comes to a big idea. The idea is what? The idea you use the limit of this rational sequence to define the irrational number. So that's the idea behind the theory, okay? But there is a problem. Now, what do you mean by limit? We haven't defined the limit is, but roughly speaking, I can see that a limit means a sequence of number approach to something, right? But later we're going to define the limit, of course. But however, this is the idea. So we can use somehow the limit to define the irrational number. Okay. So let's take a closer look. So I'll put this number on the axis, okay? Axis, you can see that, so you can see this number getting closer to some limiting point. So this limiting point is light blue, colored by light blue. It's a limiting point, okay? Now, if you plot all these points into the real number axis, so you can visualize the situation. So what we're trying to justify is that, okay, this irrational number, okay, should be considered as the limit point or this rational point, right? Okay, now we come to our original questions. Does such a point exist? Do you think this point always exists? So from the common sense, we see that this should exist. There's no problem, right? But from mathematical point of view, that's not enough. That's not enough. So what can we do with it? So this is, so we come to a point is that where we have touched the basic things, the very fundamental issue with the number theory. And that things which cannot be justified, you have to make it as an assumption. So basically we have to assume that those limit points always exist, okay? So this is something we need to assume in order to develop the real number theory, okay? But however, there's an issue, again, issue is that you cannot use the concept limit yet because the limit itself needs to be classified, needs to be defined, okay? So this means that we have to define something more basic or more basic things. Then we start with a more basic concept, more fundamental concept in order to develop this limit concept, okay? So this is what we're going to talk about today. I mean, the first concept in chapter 1. So this real basic and fundamental concept we need to assume is called a completeness property of the real number. So this completeness property is the assumption we need to make before we can develop the theory, okay? Now it's assuming this completeness property. So this property will basically guarantee the existence of limit point, basically. Okay. But however, the things itself needs to be assumed, okay, and cannot be justified. You have to accept it. It's a fact. Okay. All right. So now let's look at the bigger picture. So first we are going to lay down the completeness properties, okay? And this is our background of the whole analysis. So on that, we're going to talk about the real number series, and then you can build the whole entire mathematical analysis. Okay, so the basis of this is called a completeness property. And actually, this is called the axiom. I mean, the completeness property is something you need to accept. It's called an axiom. Okay. Now, in mathematics, there's a lots of theories, and every theory has some fundamental axioms. I'll show you examples, like axioms of Euclidean plane geometry. There's 5 of them. Okay, you have to assume all of these, then you can develop the plane geometry. Okay. For instance, the number 5. So some of these are very basic. So it's in common sense, you see this has to be right. So you have to, but however, mathematically, you are not supposed to justify. Instead, you accept this. You accept them. Okay. So here we're in the same situation. We have to first introduce the completeness property. We have to accept these properties. And then you can build the entire analysis theory, including the real number theory. Okay. Okay. So now let's begin the real things in this class. I mean the first lecture, the real material, the things we are trying to cover today. Okay. The completeness properties. Okay. Now, in order to define these completeness properties, I have to first introduce a number of things. Okay. Now first, so there's a 1.1 definition, the first definition. So let's say that you have a S in R. R is a real number set, the real number. S is a set. Okay. So we're not talking about any special set, just a general set. So it's a set of real numbers. Oh, set of real numbers. Okay. Okay. A set of numbers, basically. Now a number U is said to be an upper bound of S. Okay, so it is a constant upper bound. If for any S in this set S, S is less or equal than U. So this is a U. So upper bound is a very simple concept. If you give me a set of, if I can find any number greater than any element of this set, then that number is considered as upper bound. Of course, for some set, the upper bound may not exist. For instance, the set goes, the point in set which approaches to infinity, then there's no way you can find upper bound, right? Okay, but anyway, so if such a number exists, we are going to consider this upper bound, okay? So if a set has an upper bound, okay, then the set is considered to be bounded above. So here in this definition, part A, I have introduced 2 concepts. One is called the upper bound, the other called bounded above. Okay, it's a basic concept. For instance, suppose you consider S equal 1, 2. It's an interval 1 to 2, okay, open intervals. So any number greater than or equal to 2 is going to be an upper bound of this interval, this set, obviously, okay? And for instance, more specific, like 2 and 5 and 10, they are upper bounds of the set. And here, especially we pay attention, if you have an upper bound, then you obviously can see that there's always a smallest upper bound. Like in this case, 2 is the smallest upper bound. Okay, so if you look at the picture, so S is an interval. Then you get red bars. They are all the upper bound. And you can see on the right side is the smallest upper bound. Okay, so this is an important thing we're going to talk about later. So this is how we talk about upper bound and bounded above. And And for the same reason, and we can also introduce on the other side, the left side, then you can talk about the lower bound and bounded below. So that comes to the definition part B. Okay. If you have a number W, it's said to be lower bound if actually it's on the lower side. Any number in S has to be greater than or equal to W. Okay. And if S has a lower bound, then S is considered to be bounded below. So this is a very parallel, the same similar concept. Okay, it's parallel. Okay, so you can see for the same example, S equal 1, 2. Then you can see any number smaller than or equal to 1 is the lower bound of this interval, and -10, -5, and 1 they're all lower bound. And among all these lower bound, you can see that there's a greatest one. So 1 turns out to be the greatest lower bound. Okay, in both concepts, the smallest upper bound and the greatest lower bound, these are two important things where we want to focus on. Okay, so from the picture, you can see that when we talk about the lower bound, so this is on the left side, okay? Now, so far, it's a very elementary concept, okay? So what we're trying to introduce here is just a name, and the things behind this name is extremely simple. So that's the definition 1.1. I don't see any problem, right? Okay. So now let's consider some more examples, like S now equals to -infinity to 1, closed on the right side. Okay, so this is a interval again. Now, when we talk about S is not always has to be interval, can be any set. But for the convenience, and I can describe this other kind of non-interval set. So I just use interval as an example, simple example, to demonstrate the ideas. Okay. Now, upper bound. So you can see any number greater than or equals to 5, they are the upper bound. And so therefore, this set is bounded above. Okay, because it carries upper bound. And no lower bound, because the set extended to the -infinity. So therefore, this set is not bounded below, but it is bounded above. Okay. Similar example, -2 to the infinity. Then on the other side, lower bound exists. Okay. The lower bound, any number smaller than or equal to -2 is its lower bound. So this is bounded below and no upper bound. So therefore, the set is not bounded above. So you can have all different kind of sets. Okay, for any set, you can tell whether it is bounded above or bounded below. Okay, and well, of course, you can have set like a set from -infinity to +infinity, the whole number set, the whole number set. Then you can see this set is not bounded above and not bounded below. Okay. All right, so this is about the upper bound and bounded above, bounded below. So this is a basic concept. Now we'll come to the 1.2 definition. Okay, so continue. I'm going to introduce the names. Okay, mathematically they are very simple. So again, I consider S is a set. Okay, in R is a set. Okay, now if S is bounded above, so this means that this set has an upper bound. Okay, suppose this set is bounded above, then now we talk smallest. Okay, be very careful here. Look at the sentence here. What is it? The smallest upper bound, or another name called it's called the least upper bound. Okay, when you talk about smallest upper bound and the least upper bound, they are the same. They talk about the same thing. Now the keyword here, if exists. Now at this time, when a set is bounded above, I know that the set has lots of upper bound, right? There's no problem. But whether the set has the least upper bound, the smallest upper bound, I don't know. At this time, I don't know. Although from common sense, such things they always exist. But we're not assuming that. We only assume that we're not assuming that the set is always carries smallest upper bound if it is a bounded above. We're not assuming this, okay? So in this concept, we assume that the set is bounded above. Okay. And then we make another assumption. Another assumption is that if the smaller upper bound exists, then this smallest upper bound, I'll give it another name. It's called supreme of S. Just for a second. Okay, so in this definition, what we are doing here is just introduce a concept called supremum of S. What is supremum of S? And it's shortened by SUPS. It's basically the least upper bound or smallest upper bound. Okay, so when we made this definition, we're assuming that the smallest upper bound exists. Okay, and similar, for instance, you take into 1, 2. Okay, the sup 1, 2. In this case, the smallest upper bound exists, just equal to 2, right? So the supremum of 1, 2 is equal to 2. The supremum of infinity to phi is equal to 5. Okay. Now, similarly, I can define another name. So if S is bounded below, okay, then the greatest lower bound, okay, if it exists, it's called it's called an infimum. It's called an infimum Fs, and which is now denoted by INFS. Okay. So this is a definition in which I actually define 2 additional names. Okay, it's called supremum of S and infimum of S. So supremum S is for set which is bounded above. The other one is for set which is bounded below. But the key assumption is that we're assuming the smallest upper bound exists and the greatest lower bound exists. If they are both exist, then this thing is called supremum of S and infimum of S. Okay. Okay. So far we have talked about the definition, and also you can see this example. So they are very simple. Okay. Now we come to the completeness of properties. So what is completeness of property? So completeness of properties consists of 2 properties. One is called supremum property. The other one is called infimum property. Okay. So 1.3 is supremum property. Supremum property simply say that any. So here we're dealing with the non-empty set. We're not talking about empty set. Okay. Every non-empty set which is bounded above, has a supremum. So you can see that there's the completeness property here is just assuming that the smallest upper bound always exists if the set is bounded above. Okay, so this is the basis for the analysis and the basis for the real number property. The real number theory. The second one is called infimum property. Infimum property is saying that every non-empty set of real number which is bounded below carries an infimum. That always carries the greatest lower bound. So completeness property is very simple. It's just tell you the existence. Okay, by our common sense we know they exist, but mathematically they just assume that these 2 things exist: the greatest lower bound and the smallest upper bound. So this is called a completeness property. Okay. Okay. Any questions? So far, we are talking about only the concept. Okay. Okay. Here, I want to indicate one important thing, okay, which is not carried in the book, not written in the notes, okay. Now, we have 2 properties, okay, forms the completeness property. But however, the infimum property can be considered as a consequence of supremum property. Now, what does it mean? I mean, this means that if I accept the supremum property, itself only, okay? Then from the supreme property, I can use a logic proof to show the inferior property. So these two properties are related, okay? I don't have to assume both of them. I only need to assume one of them. Then I will automatically be able to get the other thing. So this is the things I want to show you first. That means I want to show you how you can go from the supreme property to the inferior property, or vice versa. Okay, I want to show this process, and this process is a proof. And this is by going through this process, actually I review with you some of the proof argument. Okay. Okay, so every time we want to do proofs in this class or in the analysis, mathematical analysis, you have to think about it first, okay, to find an argument. And sometimes draw some picture will help you. So this is what I'm trying to do. Okay, we want to prove that suppose I have supreme property, then automatically I can get the inferior property, okay? So let's say that, so what we really need to prove, we need to show that the greatest lower bound always exists, okay? So therefore, let's take a look at this situation. You have a set S. Okay, this set S, so this set has a lower bound. So I use the red bar to show you. So on the left side, left end, so there's a lower bound. Well, what we really need to show is that this set also carries the greatest lower bound, right? But at this time, I don't know. But what we really have is a supreme property. Supreme property says that if the set is bounded above, then that set will carries the lowest upper bound, right? So, but here we're dealing with opposite case, right? It's on the lower side. Now, how do you do it? So mathematically, the idea is we want to convert this case to the other side. Okay, convert this lower bound case to the upper bound case, and this can be done very simple in a very simple way. You can actually reflect the X, make a reflection of S to the other side. So it's called minus S. That means you put a minus sign to every number in S. So a new set is called minus S. It's a new set, right? And this new set, you can see that it's a reflection through the origin, right? It's a reflection. You can see the red bar will be reflected to the right side of the minus S. So this process simply tell you is that now the minus S has an upper bound. Previously, the S has a lower bound. Now you can see minus S become bounded above, okay? And then you can see for the minus S, you can apply the supreme properties, because supreme properties say that there is a least upper bound for minus S. That's coming from supreme property. Okay, once you get this, you just reflect back. Then you can see the green bar. The green bar become the greatest lower bound. Okay, so that's the idea of the proof. Okay, you have to do this reflection, so you can turn the situation, the lower bound case to the upper bound case, to apply the supreme property. Then you transform back. So once you transform back, you get an inferior property. So that's the basic idea. So I'm now going to write down the detailed proof for that, okay? So step one in the proof, we want to make a transformation, okay? So you let S here, we begin to prove it. We let S in R, okay, which is bounded below. And then you let W to be arbitrary lower bound of S, okay? We need this to be arbitrary. There's no special property associated to W, just arbitrary lower bound S, okay? So for this lower bound, you can see that S is greater than W for all S. So here we are just repeating the definition of the lower bound, right? Okay, then I'm going to make a reflection. Now, how do you make a reflection? You are defining a new set we call minus S. So I'm defining now the minus s to be, I use set language, okay? The minus s equals to minus s for s in the original set s, okay? So that's the set of minus s is defined. This. Then you can see the minus s is bounded below or bounded above. Why? Because you look at the previous inequality. So you put minus sign to that inequality, you get minus s is less or equal than minus w. Okay. So this means for every minus sign in the minus set, this number is controlled by minus w. So this simply says that minus w is upper bound of minus s. So this way you show that the minus s is bounded above. Okay. And now you begin to use the supremum property to the minus s. So by the supremum properties, there is a supremum u for minus s. Okay. What does it mean? This means that the minus s is less or equal than u for any s in S. And also, u is less or equal than minus w. Now you can see minus w is arbitrary lower bound from very beginning, right? After the reflection, so minus w will become arbitrary upper bound for minus s. And u is the least upper bound. So u is obviously less or equal than minus w. Okay. Okay, so we apply the supremum property to the minus s, and now we reflect back. Reflect back if you look at the fourth picture. And then you can see that if you, from the previous inequality, you can see if I put the minus sign back, you get s is greater or equal than minus u for any s, okay? And also minus u is greater or equal than w. So just adding minus sign to both inequalities, so I'm getting new equality. And these two new equality will simply tell us that minus u is the lower bound of s. So we're not talking about minus s, we're talking about the s. It's the lower bound of s, okay? And this is greater than or equals to arbitrary lower bound w. W is an arbitrary lower bound. So they simply say that minus u is the greatest lower bound of s. So this will finish the proof. So here I'm just using this opportunity to show a proof. I may help you to understand some of these arguments. I mean the argument we use in the proof. Okay, and that's imply that once you assume the supremum property, so this property can be used to derive the infimum property. So the conclusion is like this. The conclusion is that if you look at the background, okay, the basis for the mathematical analysis, and you can just assuming the supremum properties instead of assuming the completeness property, okay? Because the supremum, once you assume the complete supremum property, and this will imply the infimum property. Therefore, you get a completeness property, and that's enough. So this is the minimum assumption we need for the mathematical analysis, okay? Okay, any questions? And if you have problems or questions, you can answer anytime. I can review, I can always go back to clear some of your doubts or solve some of the issue. Okay, I still have time today. Okay, I have an additional 15 minutes. I think I will go through one theorem, okay, that 1.5, that's the first theorem we'll talk about. That's called I mean, suppose you say something is called a supremum property, right? Supremum something. Sometimes this definition is kind of abstract, Okay, we want to use some other language to describe the supremum. So that's the things we want to talk about. Okay. Let me see. So so once I finish this one, so we're done. Okay, if you have any question, we can also talk about during the office hour and another time. So let's say that you have a S. So let's say S is a non-empty set. Okay. Now here, a number is a supremum of F, if and only if the following two properties hold. So what this theorem is saying is that we can use two other properties to define the supremum of a set. Okay. So what is these two properties? It means that the first one is that there's no S in S. U is less than S, strictly less than S. So that's property one. The property two is that if V is less than U, then there is a SV. SV, S sub V is mean a special point in S, such that V is less than SV. It looks like we're making things too complicated, right? Because you can see supremum is a very clear concept. And now we're talking about two properties, property one and property two. So what I'm saying is that this supremum concept is equivalent to one plus two. Okay. But here, and actually they're not complicated. They're very simple. Okay. So you look at this picture. Okay. Now here we have situation S is a set. Okay. And then U is the supremum. That's the least upper bound. Okay. So that's the situation. So let's, from this picture, try to understand these two properties, one and two. Now, the property one is extremely simple, okay? The property one simply says that U is upper bound. So this sentence says that there's no S which is greater than U. So therefore, U is controlling every element in S. So therefore, U is the upper bound. So that's clear. The U in the property one, it doesn't necessarily imply that U is the least upper bound, but at least it tell you is that U is upper bound. So that's the message from one. Now, what is the message from two? You look at second picture. So when we have a V is less than U, this means that V is on the left side of U, right? There's a gap between V and U. Okay. Now, if you have a V something like this, you can see since U is upper bound, the least upper bound, okay, then V cannot be upper bound. V cannot be upper bound, right? Okay, so this means that there must be something between V and U, okay? So anything you pick between U and V, so that thing, what we call is SV, S sub V, is going to be greater than V. Okay, so the property two is just tell us that U is the least one. You cannot have anything lower than that. So the property one tells us that U is upper bound. Okay. The property two showing that U is the least one. So therefore, these two properties together show that the U has to be supremum of S. Okay. Okay, here, so this is a very simple property. But however, we need to give a proof of this property, okay? So because you see the statement is if and only if, so you have to prove from both sides, okay? Now first, let's show that, suppose you assume that U is the upper bound, okay? U is the upper bound. And from there, we're going to show these two properties. Now, okay, so now let's begin the proof. Now, since U is upper bound, okay, we're from our assumption. So by the definition of upper bound. Now here, when we say that, we are not using the fact that U is the least upper bound, okay? Just assume from here, you can see that U is upper bound. And so by the definition, you can see every S, every element in S is less or equal than U, right? So you can say that there's no S in the set such that U is less than S. So this is just proof 1. So you can see the probability 1 is very simple. It's a direct consequence of the fact that U is upper bound. Okay. Now for the second probability, you need to use the fact that U is the least upper bound. So now let's set V is less than U. Okay, you pick a number, it's less than U. And then since U is the least upper bound, okay, now here the key thing is that you have to use the fact that U is the least upper bound. So V is no longer upper bound because U is the least one. How come, and V is less than U, how come U is another upper bound? That's impossible. So V is not upper bound. Now, if something is not upper bound, so this means that there must be some elements it's greater than V. So that's what we come up with the S sub V. So this proves the probability 2. So you can see that in this direction, we use the fact that U is upper bound and also the least one. You can get these 2 properties, okay? But this is only halfway done, okay? Because the proof is if and only if. The second part is the other side. The other side is that we're assuming 2 properties, 1 and 2. And from these 2 properties, we want to show that U is actually a least upper bound. So therefore in this direction, using these 2 properties, we want to show that U is upper bound and also U is the least upper bound, okay? Then you can conclude that U is a supremum. 1. So let's begin with probability 1. So I'm going to use these 2 properties one at a time, okay? The probability 1 implies that, a direct consequence is that U is always less than U, or S is always less than U for any element in S. So this probability simply says that U is upper bound, okay? And then I use the probability 2. Now probability 2 implies that for any other number less than U. So this second probability just saying that V is not upper bound. So therefore the second probability implies that U is the least upper bound. So therefore, which is the supremum of S. So you can see these 2 probabilities are sufficient to imply that the U is the least upper bound. So that's the proof of this property, the supremum property. Okay. And this is, so the previous property is called, the theorem is called a characterization of the supremum. And we have a similar result. It's called characterization of the infimum. It's similar to that because, again, we assume S is a non-empty set. Okay, then we argue with the infimum of F. So U is the infimum of S if only if you have these 2 properties. Similar, it's actually the parallel properties. Okay, maybe the inequality sign is opposite. Okay, so I'm not going to show this proof, but instead I'm going to assign the 1.6 as a theorem as the exercise 1. So this is something you need to think about it after the class, and we'll want to come back to this theorem in the next lecture. All right. So this is all I have to say, and I have actually assigned the homework. That's the exercise number 1. Any questions? Are you comfortable with this kind of presentation? I wish to hear from you so I'll make sure that I'm doing something right.
Yeah, I like the presentation method. I think your notes are
Okay.
good.
All right. Okay, that's good. Yeah. Okay. Spend some time working on this exercise one. As I said, it's very important for you to do the homework after the class. I mean, right before the next lecture. Okay, then you can understand. I mean, you can review this lecture, and also you can understand more about the arguments. Okay. Okay. Okay, so that's it for today. So in 15 minutes, so I'm now going to closing this unless you have any further questions. And in 15 minutes, I'm going to begin with the office hour, the same link. Okay.
I was curious where you will be posting the link for the YouTube channel, or if there's just a way that we look that up at all.
You mean the recording?
Yeah, just for future studies, like checking in on our notes afterwards. I like to go and watch it twice, really, but that's just me.